So today we're going to cover the concept of stress, Cartesian stress, and stress transformation. So stress is a measure of a macro level of force over a cross-sectional area of a body. This force over area measurement is what we call stress, and it's in units of Pascal, which is newtons over meters squared, or it can be pounds over inches squared, which is PSI. Generally, when we're thinking about stress that's distributed to through a body, we can think of it in different ways. Um, Under axial loads, where we have forces that are perpendicular, that are uniformly perpendicular to a cross section, we have a uniform distribution of stress through a cross section. While if we have a beam that's subject to like a bending moment, instead of having a uniform distribution of stress, we can have a non-uniform distribution. In terms of moments, a linear distribution where one side of the beam stretches and is in tension, and the other side of the beam is in compression, right? So stress can either be uniform or non-uniform in a body. Now, if we were to take some structure, some complex structure, and we've loaded it up with a lot of different forces and moments, um, and we take one unit cell of that unit cell is subject to what we call a state of stress, where stresses can be applied perpendicular to the surfaces of the unit, but also there can be shear stresses that go across those surfaces of that unit cell. And this results in what we call the stress tensor, which is the state of stress within any particular unit of a body. Now, this state of stress, this tensor, has 6 terms. 3 of them are diagonal, so the normal stress on the x surface, normal stress on the y surface, normal stress on the z. And then there are shear stresses that are applied, tau xy, where x is the surface and y is the direction, tau xz, the x surface, the z direction, and then tau yz, which is the y surface and in the z direction. Now, in order for equilibrium to hold true, these shear stresses that are applied on a certain side of the body must be balanced by equal shear stresses, equal and opposite shear stresses on the other sides of the unit cell. And so in total, there's actually 6 terms of stress that we have to be concerned with. The diagonal terms are the normal values, and then those balanced shear terms, which are equal to their opposite neighbors, right? So these terms across the tensor are equal, right? Now, 3D stress, it's a lot to deal with. We're dealing with the stresses applied in all 3 dimensions. But often, we can simplify a problem from 3D to a simple 2D problem. And that's where we have the case of 2D plane stress, where stresses on one plane in the body go to 0. Say stresses in the Z direction out of the page are 0. In that case, our stress tensor simplifies to simply 3 terms. There's a normal stress in the X and the Y direction. So on the on the X direction and the Y direction. And then there are shear stresses, tau xy and yx, that are applied equal and opposite in order to maintain that equilibrium, right? And this 2D stress is typically what we work with a lot in, mechanics of materials, and mechanical design. It makes it a little bit easier for us to solve problems. Now, another important thing we need to note when we're looking at these stress elements is how to figure out what is a positive sign convention. So if we were to draw one of these elements, what sense is positive, what sense is negative? So let's say we have a stress element, and let's examine the surface, the positive x surface. If we have a shear stress that is applied, that's going to give us a counterclockwise sense of rotation, with respect to this positive x surface, then that is going to give us, that will define that as a positive shear stress that's applied to our body. If we have a positive x surface and the shear stress is going to give us a clockwise sense of rotation of our body, then we'll define that as a negative shear stress. So it's important, if you were to just be given a problem like this, but with actual numbers for the stresses, you'd be able to know what's positive, what's negative. That's key, right? So now we got these stresses in hand. There's a body, it's loaded up complexly. We've pulled one of the, a unit, a subunit from it, and we've got this state of stress. Now, what do we do with this stress tensor? Well, what can we do with it? Well, let's start with transforming. Let's start with stress transformation, where we have this stress element, 2D, and we decide to section it. Let's section it at some angle, exposing the internal normal and shear stresses along that section line. If we perform that operation and then do a little bit of math, we can describe the internal normal and shear stresses as a function of that angle phi as follows, where the normal stress sigma is equal to sigma x plus sigma y divided by 2, plus in brackets sigma x minus sigma y divided by 2 times cosine of 2 phi plus tau xy times sine of 2 phi. And then our internal shear stress is equal to negative sigma x minus sigma y divided by 2 times sine of 2 phi plus tau xy times cosine of 2 phi. So these two stresses are exposed by that section, right? So that's the basis there. Now let's consider, instead of sectioning the geometry, what if instead we took our stress element and we rotated it so we could find stress in a new coordinate system? So alternatively, let's take our stress element and let's rotate it. Let's rotate the whole element by an angle phi. And let's find the state of stress in this rotated, in this primed coordinate system, in the x prime and y prime coordinate system. If we were to do a little bit of math to try to do the transformation, we'll find that the rotated state of stress, sigma x prime, sigma y prime, and tau xy prime are as follows. These following equations. And this rotated coordinate system would allow us to say, hey, if we're concerned with stresses in a body going in a particular direction, we could just transform the state of stress, and then we know, in this direction, what is the state of normal stress? What is the maximum normal stress in a particular direction through our geometry, right? Okay, so now we've got the concept of sectioning our body and exposing the internal stresses, but also rotating our body. Now let's see what we can do. Are there any special angles within our geometry that we might want to explore? So let's start with the principal stress directions. So principal stresses and their directions, they exist on planes where the internal normal stress is maximized. So when you section it, there's a maximized normal stress and the shear stresses are 0. So there exists some special angles, some special values of phi where normal stress is maximized and there is no shear stress. And we can determine it, or we can find it by either sectioning at that angle or even rotating our element at that angle. And we actually find two of them. We find two angles for our 2D problem where this condition exists. Solving the math for this, we'll be able to find those angles as tan times 2 phi p, where p means the principal direction, is equal to 2 times tau xy divided by sigma x minus sigma y. So we can rearrange and solve for the phi angle. We also will find, since we rotate our coordinate system and there's 90 degrees between x prime and y prime, that if we have one of the phis, the other is easy to find. So phi p2 would be equal to phi p1 plus or minus 90 degrees, because there's 90 degrees between them, right? So if we solve this tan, we may get one angle, and then we plug that angle in here, and we get the two. We get the two complementary angles. So for 2D problems, we have two angles, two principal directions is what we call them, and we end up with two principal stresses, sigma 1 and sigma 2. Sigma 1 is the larger value. The first principal stress is the largest normal stress that we find, and then sigma 2 is the second largest. We also need to remember that in the principal directions, shear stresses go to zero. So tau is equal to zero in this very special direction, right? Okay, so we found a set of directions. That's interesting. Let's search for another one. We found the angles where the normal stresses are maximized. So let's look for directions where the shear stresses are maximized. Let's do the same thing where we section our sample, but here we are searching for an angle where the shear stress is maximized, and in that direction or in those directions, normal stress doesn't go to zero, rather normal stress becomes an average value. So we actually have an average normal stress, an average of the normal stresses in our geometry. If we were to rotate our element, we'll also find that there are actually two angles where shear stresses are maximized, a phi s1 and a phi s2. Now, doing the mathematics, we'll find the angle phi s is tan times 2 phi s is equal to negative sigma x minus sigma y divided by 2 times tau xy. Rearranging and solving, we'll get one or sometimes two of our angles for phi s. If we only get one, then we can solve for the second by saying phi s2 is equal to the phi s that we found plus or minus 90 degrees, because again, there's 90 degrees between our two angles, right? Now for a 2D problem, what do we have? We have two extreme value shear stress directions, two angles where shear stresses are maximized. And the shear stresses, tau 1 and tau 2, the extreme values, the max values, there are two of them, and they are equal to each other, but of opposite sense. For equilibrium, tau 1 and 2 are equal to plus or minus the tau max. So they are the same number, just one is positive and one is negative to maintain equilibrium. And then that average stress that exists on our body is literally the average of the normal stresses. So sigma x plus sigma y divided by 2, right? Not too bad. So now we found a second set of special angles, right? Now, if we do a little bit more mathematics, we will find a relationship between the angles where principal stresses are maximized and shear stresses are maximized, where the phi s, or the angle for shear stress, is equal to phi p, the angle for principal stresses, plus or minus 45 degrees. That means that the extreme value of shear stresses sit at 45 degrees relative to the extreme value principal stress directions, right? What that also means is if we are able to find one set, we can very easily find the second set of important directions within our stress tensor. So now finally, what if we want to find the values, the extreme values, not the angles directly, but what if we want to actually find the principal stress values or the extreme values of shear stress? Well, there's a way that we can get directly to those values. If we do a little bit more mathematics, we can find a direct solution to the principal stresses, where if we plug the principal direction equation into our normal stress equation, we can find the first and second principal stresses, sigma 1, comma 2, is equal to the average stress average normal stress, sigma x plus sigma y divided by 2, plus or minus the square root in brackets of sigma x minus sigma y divided by 2, all of that squared, plus tau xy squared, right? This is in essence equal to the average normal stress plus or minus the extreme valued shear stresses, right? And then our extreme valued shear stresses, if we want to just get directly their value and not worry about the angle, then that is the second term. So the tau 1, 2 is equal to plus or minus the square root term. And there should be a squared on this. So that's squared, which is also equal to the first principal stress minus the second principal stress divided by 2. So now we've got a way to go ahead and directly just get those values, the extreme valued values for any 2D stress tensor. Now let's think about how would we use these equations. If we're given a problem and we just want to find directly the principal stresses or the extreme values of shear stress, then we should just go ahead and directly use these equations. If that's our only concern, what is the principal stress? But if we're being asked to find the values and the directions, so we want to find not only the principal stress value, but its direction in a body, then we need to go further back and first apply the tan equations to find tan times 2 phi p and 2 phi s, and then plug those angles in to the stress transformation equation to find the extreme values, right? And with that said, we've got the basis of stress. We learned about stress transformation, both by sectioning a body or rotating a body, and we learned about two special directions. The directions for principal stresses, where normal stress is maximized, and the extreme valued shear stress directions, where shear stress is maximized.